droplet diameter. So typically people fit a log normal profile, but some of these data are not very accurate in this small droplet size. We believe that the small droplets should be even larger. They're harder to measure, perhaps. So a very good model will be what is called a Pareto distribution. It's a very simple distribution. And this Pareto distribution can be used from some minimum diameter, say 1 micron, to a large diameter, say 1 millimeter. So this is how the droplets are first ejected. The theory I'm going to show doesn't care what distribution you're going to follow, but let's say that Pareto distribution is a good distribution. The other thing I want to talk about is that if you zoom in, and this is the, say, 100 micron droplet that comes out, most of it is water, but there is a non-volatile material in there. This non-volatile material may be mucus, food particles, and most importantly, it also contains these virus particles. So when a droplet evaporates, it evaporates pretty rapidly. Whatever non-volatile is that's there will still remain, and it will be sort of like more like it becomes eventually into a particle or an aerosol, and it will stay airborne. And I will call this leftover particle to be droplet nuclei. Okay. So in some sense, the ejection condition tells us sort of some few parameters about the hot puff of air that comes out. The puff is characterized by a typical like a jet theory or a plume theory by a volume, how many liters are put out, what's the momentum in terms of velocity and buoyancy. Whereas the droplets themselves are characterized by the Pareto distribution, for example, and how many droplets and what's the volume, and what fraction of the droplets is really the non-volatiles, and what fraction of the non-volatiles are the virus particles. So those are the important quantities to pay attention to. Before I talk about the theory, I just want to show some simulations that we have done. These are large eddy simulations. We have done many simulations, but I just want to show you some sample example. So this is one particular case, not a very intense cough or sneeze. So this is about half a liter of hot air that comes out, and droplets are ejected from 1 micron to 1 millimeter, and the bigger ones you can see rain out. This is about 11 seconds. In 11 seconds, it doesn't travel a whole lot because the velocity is very modest and the volume. But later you can see that if there is cross ventilation and there is ambient turbulence, this puff gets carried. And this puff contains a lot of droplets. So those are the important things. So there is entrainment. The puff gets larger in size because it entrains ambient air. There is a clear fallout of droplets. There, you can't see it, but these droplets have become much smaller than what they were ejected, and they stay floating. The whole process is chaotic. And then because it's hotter, it later on rises up slowly, and that's one other reason